Evenings are the beautifully sweet spot between the harsh light of the day and the dead darkness of the night. Good evening to one and all present here. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome all the PG students and CSIR aspirants. Prayer does so many things. It heals, comforts, strengthens, and brings you faith. Now, Tamuttai Vartu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
This is C4 workshop, Chase, Crack, Conquer, CSIR Net, which will make the CSIR aspirants to go to the next level. I am very proud to introduce our resource person, Dr. S.P. Vijayalakshmi, Assistant Professor, PG and Research Department of Mathematics, DG Vaishnav College. She has completed UG from SDNB Vaishnav College and PG from Meenakshi College, MPhil from Meenakshi College. She has completed PhD from Bharatiyar University, Coimbatore. She has guided 6 MPhil students and published 8 papers in international journals. Welcome, ma'am. Now I hand over the session to you, ma'am.
Is the screen visible? Is the screen visible, sir?
Yeah,
Am
ma'am.
I
Now
on?
okay. Yeah, okay, ma'am. Now okay, ma'am.
Okay, thank you, sir. Good evening to everybody. So, in today's class, we are going to discuss about the complex analysis. So, this is the 18th session. So, complex analysis under Unit 2, here we have algebra of complex numbers, complex plane, polynomials, power series, transcendental functions, and then Cauchy-Riemann equation, contour integral, Cauchy theorem, Cauchy integral formula, Taylor series, Lorentz series, Cauchy residues, etc. So actually this is a pattern. So in part A, 20 questions will be given and you have to answer 15. So for part A and part B, you have the negative marking, and whereas part C, no negative marking. So in complex analysis, the question will be based on the complex integration, residue, singularity, meromorphic function, analytic function, bilinear transformation, conformal map, etc. So these are the important topics. So in the upcoming classes, we'll be discussing about this analytic function, power series, complex integration, Schwarz lemma, bilinear transformation, Cauchy's theorem, and the problems based on the maximum and minimum modulus principle, etc. So in today's class, we will discuss about the singularities and the residue theorem, the first two topics. So before going into the problems, we will study the basic concepts. So that is the basic definitions and the basic theorems. Okay, so applying this definitions and the theorems, we can solve the problems easily. So first we will see the basic definitions. So everyone know the single valued function. So the function is said to be single valued if there exists only one value. Otherwise, it is said to be a multi-valued function. For example, if you consider f of z equal to z square, f of z equal to z squared is a single valued function, and f of z equal to root z is nothing but the multi-valued function, because if you put z equal to 4, we'll be getting plus or minus 2. So it is said to be a multi-valued function, right? And then the differentiability in a region. That is, if a function is differentiable at all points in a region, then you can say that it is differentiable at the region. And similarly, analyticity at a point. That is, we say that the function is analytic at a point if it is differentiable at all points in some neighborhood of a point. So if the function is differentiable at all points in some neighborhood of a point, then you can say that the function is analytic at that point. And if the function is analytic at all points in the region, then you can say that it is analytic in the entire region. So the next comes a singular point. So singular point is nothing but the function ceases to be analytic. The point at which the function is not analytic is nothing but the singular point. So in singular point, we have the isolated singularity. So isolated singularity means, that is, if suppose z equal to a is a singular point, and if there exists a neighborhood of z equal to a containing no other singular point, then you can say that z equal to a is a isolated singularity. That is, in the neighborhood, no other singular point should exist apart from A. Then you can say that it is a isolated singularity. For example, suppose if you consider the function 1 by z into z minus 1. So here 0 and 1 are the singular points and they are isolated, right? So this isolated singularities are further classified into three types. That is the removable singularity, pole, and then the essential singularity. So in the Lorentz series, the principal part is nothing but the part containing the negative powers. So the negative powers is nothing but the principal part. So if there is no principal part, that is, if there is no negative powers of z, then you can say that it is a removable singularity. So if the principal part has finite number of terms, then you can say that it is a pole. And if it has infinite number of terms, then it comes under the essential singularity. So isolated essential singularity, that is infinite principal part. So that is nothing but the isolated essential singularity. So here we have non-isolated essential singularity. So non-isolated means the limit point of the sequence of poles is said to be the non-isolated essential singularity. Okay. Now, suppose if you consider the function tan 1 by z. So the poles at points. are given by z equal to 1 by n pi. Okay, the limit point of this sequence of poles is z equal to 0. Therefore, you can say that this is a non-isolated essential singularity. So based on this singularity, we will do some problems under part B and part C. So we all know that in part B, you have only one option will be correct, whereas in part C, multiple options will be right. Okay, so you have to work out all the options in the part C. So here we are going to discuss the nature of singularity at z equal to minus 2. For the function f of z equal to z minus 3 into sine of 1 by z plus 2. So we need to find the nature of the singularity, that is whether it is an essential singularity, pole, or removable singularity. So first we will find the zeros of the analytic function. So how to find the zeros? So the zeros of f of z is given by z minus 3, that is f of z equal to 0. So just if you equate, you will be getting z equal to 3 or sine of 1 by z plus 2 equal to 0. So from this you can say that 1 by z plus 2 is nothing but n pi, because sine n pi is 0. So from this you can say that z equal to minus 2 plus 1 by n pi. So the limit point of 0 is minus 2, and therefore you can say that z equal to minus 2 is a isolated essential singularity. So we'll go to the next problem. So if you consider the function f of z equal to z minus 1 divided by e power 2 pi I by z minus 1, then which of the following are right? Okay, so this is a part C question. So we need to find all the correct options. So the first option is f as an isolated singularity at z equal to 0, f as a removable singularity at z equal to 1, f has infinitely many poles, and each pole of f is of order 1. Okay, so in this 4 options, we need to find what are the options are right. So first we will take the function. So f of z equal to z minus 1 divided by e power 2 pi I by z minus 1. So here if you equate the denominator to 0, here you are getting e power 2 pi I by z equal to 1. So if you take log on both sides, you can simplify and you will be getting z equal to 1 by k. So in this points, the function is not analytic. That is, these are the singular points. So the first option. So what is the first option? F has an isolated singularity at z equal to 0. So since z equal to 1 by k, as k tends to that is when as k tends to infinity, z will be tending to 0. Therefore, you can say that the first option is false, right? Because what is the first option? F has an isolated singularity at z equal to 0. So this is not right. We will check the next option. So the next one is limit z tends to 1, z minus 1 divided by e power 2 pi I by z minus 1. So as limit z tends to 1, z minus 1, you'll be getting 1 by of this, right? That is, if you directly apply the limit, you'll be getting 0 by 0 form. So let us apply the L'Hopital rule. So you can differentiate the numerator and the denominator separately. Okay, so applying that rule and then apply the limit. So as z tends to 1, you'll be getting minus 1 by 2 pi I. Okay, so what is a removable singularity? That is, limit z tends to a f of z should be finite, or you can say limit z tends to a z minus a into f of z equal to 0. So clear? So this is a removable singularity. So now the C option we will check. So limit z tends to 1 by k of this. So again, if you apply the limit, you are getting 1 by 0, so which is equal to infinity. So you can say z equal to 1 by k are the poles. Because as we know that a limit z tends to a f of z equal to infinity, then you can say that a is a pole of f of z. So the last option is D. So limit z tends to 1 by k, z minus 1 by k into f of z. Because what is the D option? Each pole of f is of order 1. So we need to check the order now. So the order of the pole is limit z tends to a, z minus a the whole power k into f of z is not equal to 0. Then you can say that the order is k. So we will check the last option, that is the D option. So So limit z tends to 1 by k, z minus 1 by k into f of z. So as limit z tends to 1 by k, substitute the function. So again you are getting 0 by 0 form. So again applying the L'Hopital rule, and then you have to simplify. So if you simplify, you are getting this answer, that is 1 by k minus 1 into minus k square divided by 2 pi I. So this will be not equal to 0 if k is not equal to 1. Okay, when k equal to 1, this will be equal to 0. So clear, but k cannot be equal to 1 because z equal to 1 is a removable singularity. So you can say that when k is not equal to 1, you are getting this is not equal to 0. So clear, therefore you can say that option B, C and D are right. Okay, so A is false and B, C and D are true. Yes. So F has a removable singularity and F has infinitely many poles and each pole is of order 1. So B, C and D are true. So this is a part C question. Okay, we will go to the next problem. Suppose if you consider D equal to Z belongs to C such that mod Z is less than 1 with a unit disk, and F is a function from D to C, B an analytic function satisfying f of 1 by n equal to 2n divided by 3n plus 1 for n greater than or equal to 1. Then which of the following are right? That is f of 0 equal to 2 by 3, f has a simple pole at z equal to minus 3, f of 3 equal to 1 by 3 and no such f exists, right? So here the function f of 1 by n, so 1 by n is given to be 2n divided by 3n plus 1, right? Suppose if you put 1 by n equal to w, then you will be getting f of w equal to 2 by w and then 3 by w plus 1. So just simplify this. So what is f of 0? So if you put f of w equal to 0, you will be getting f of 0 equal to 2 by 3. Okay. So when w plus 3 equal to 0, you are getting w equal to minus 3. So you can say that this has a simple pole at w equal to minus 3. And also you can check that f of 3 will be equal to 2 by 6. So 2 by 6 is nothing but 1 by 3. Right? So the options are, these two options are right. That is f of 0 equal to 2 by 3 and f of 3 equal to 1 by 3. Right? So A and C are true. Suppose if you consider this question, that is at z equal to 0, the function f of z, which is equal to e power z plus 1 divided by e power z minus 1. So this function will have a removable singularity or a pole or essential singularity, or the residue of f of z at z equal to 0 is 2. So we need to check which of the options are right. So first we will check the first one. So limit z tends to 0, z minus 0 into f of z. So z minus 0 into f of z. So what is z minus 0 into f of z? So limit z tends to 0, z into e power z plus 1 divided by e power z minus 1. Okay, so that is limit z tends to 0, z divided by e power z minus 1 into e power z plus 1. So if you apply the limit, you will be getting 2, which is not equal to 0. So you can say that z equal to 0 is not the removable singularity of f of z. So when e power z minus 1 equal to 0, then you can say that e power z equal to 1. So 1 is nothing but e power 2n pi I. Okay, n takes the value 0 plus or minus 1 plus or minus 2 and so on. Right? So you can say that z equal to 0 plus or minus 2 pi I plus or minus 4 pi I, etc. are simple poles. So you can say that z equal to 0 is not an essential singularity. Right? So since z equal to 0 is a simple pole, therefore you can say that z equal to 0 is not an essential singularity. Now you will find the residue for at the point z equal to 0. So what is your f of 0? Limit z tends to 0, z minus 0 into f of z. So limit z tends to 0, z minus 0 into f of z is nothing but 2. So you can say that the option B and D are true. So it's a pole and the residue at z equal to 0 is 2. Okay, so these two options are right. Okay, and then we will see what is a residue. So residue is nothing but from the Lorentz series you can find the residue. That is, suppose if z equal to a is an isolated singularity of f of z, and if the Lorentz expansion for f of z about z equal to a is summation a n z minus a the whole power n, then the coefficient of 1 by z minus a, or you can say that z minus a the whole power minus 1, namely a minus 1, is called the residue of f of z at z equal to a. It's called the so here you can find the residue. That is, suppose if z equal to a is a simple pole, then you can find the residue at z equal to a as limit z tends to a z minus a into f of z. So this is how you can find the residue of the function at z equal to a if z equal to a is a simple pole. Suppose if z equal to a is a pole of order m, then you can find the residue of f of z at z equal to a as 5 power m minus 1, that is a derivative of a divided by m minus 1 factorial. That is 1 by m minus 1 factorial d power m minus 1 by dz m minus 1 of z minus a the whole power m into f of z. That is, you have to find the m minus 1 the derivative, and then you have to substitute z equal to e. So this is how we have to find the residue. So the first one is either by using the Lorentz expansion. So in the Lorentz expansion, by considering the coefficient, you can find the residue. So if it is a simple pole, then you can find limit z tends to a z minus a into f of z. And if it is a pole of order m, then you have to find the derivative, m minus 1 the derivative. 1 by m minus 1 factorial into d power m minus 1 dz power m minus 1 of z minus a the whole power m into f of z, and then you have to substitute z equal to a. So these are the methods of finding the residue. Okay. So using that residue, we'll see one problem. Let h is equal to z, which is nothing but x plus iy, where y greater than 0 be the upper half plane, and d is a unit disk, that is mod z less than 1. And suppose if f is a Mobius transformation which maps h conformally onto d, and suppose f of 2i equal to 0, then which of the following are true? Okay, this is a part C question. So more than one option will be right. So we have to check all the options. So the first option is f has a simple pole at z equal to minus 2i, and f satisfies f of I into f of minus I the whole bar equal to 1, and f has an essential singularity at z equal to minus 2i, and modulus of f of 2 plus 2i equal to 1 by root 5. So we need to find the correct options in this. So here this is a bilinear transformation which carries R to the unit circle. Okay, so under the bilinear transformation, we know the formula. If it carries to the unit circle, f of z equal to e power I alpha into z minus z naught divided by z minus z naught the bar. Okay, where alpha belongs to R and z naught does not belongs to R. So here we have two conditions. That is, if imaginary part of z naught is greater than 0 or less than 0. So from this you can split into real and imaginary part. So if the imaginary part is greater than 0, then you can easily map, and you can say that the lower half plane maps to the exterior of the unit circle and the upper half plane maps to the interior of the unit circle. So under this bilinear transformation. Similarly, if imaginary part of z naught is less than 0, then you can say that the lower half plane maps to the exterior of the unit circle and the upper half plane maps to the the lower half plane maps to the interior of the unit circle and the upper half plane maps to the exterior of the unit circle. So in the first given that f of 2i equal to 0. So let us substitute 2i. So if you substitute 2i, you will be getting e power I alpha into 2i minus z naught divided by 2i minus z naught bar equal to 0. So if you simplify, you will be getting z naught equal to 2i. Okay, just it's an ordinary simplification. So if you simplify, you will be getting z naught equal to 2i. So in the substitute z naught equal to 2i in f of z. So f of z is nothing but e power I alpha z minus z naught. So here z naught is 2i. So I'll be getting z minus 2i divided by z plus 2i, right? Because what is your f of z? So f of z is nothing but e power I alpha into z minus z naught divided by z minus z naught bar. So here you will be getting minus 2i bar, so which is nothing but plus 2i. So z plus 2i. So now we will check the options. So first one, limit z tends to minus 2i, z minus of minus 2i. So we'll be getting z plus 2i into f of z. So if you substitute the function f of z here, and if you simplify, you'll be getting e power I alpha into z minus 2i. So which is not equal to 0. So clear, therefore the first option is right. So what is the first option? F as a simple pole at z equal to minus 2i. Okay, and then the next one, f of I into f of minus I. So f of I into f of minus I the whole bar. So f of I is nothing but e power I alpha into, just substitute z equal to I. So we'll be getting I minus 2i, which is nothing but minus I divided by 3i into f of minus I the whole bar. So here you will be getting e power minus I alpha. Because bar is there, so you will be getting minus here. So e power minus I alpha into minus 3i divided by I. So if you simplify, you will be getting 1. Okay, this is minus I alpha, because here since you have the conjugate, here you will be getting minus I. So e power plus I alpha and minus I alpha, and then 1 by 3 and 3. So this will get cancelled and you will be getting 1. So f of I into f of minus I the whole bar equal to 1. So that is your second option. That is, if satisfies f of I into f of minus I the whole bar equal to 1. So this option is right. So now we will check the third one. So the third one is false, because what is your third one? F has an essential singularity at z equal to minus 2i. So f has an essential singularity. Essential singularity, already f is a simple pole, right? So f is not the essential singularity, right? So we will check the fourth option. So modulus of f of 2 plus 2i. Modulus of f of 2 plus 2i equal to modulus of e power I alpha into, so just substitute the values. So 2 plus 2i minus 2i divided by 2 plus 2i plus 2i. So if you simplify, you can see mod 2 divided by modulus of 2 plus 4i into modulus of e power I alpha. And then if you simplify, you'll be getting 2 divided by root 20, which is nothing but 1 by root 5. So from this, you can say that the options A, B and D are true. So the A option is f as a simple pole at z equal to minus 2i, and then B, that is, f satisfies f of I into f of minus I the whole bar equal to 1, and then the D, f of modulus of f of 2 plus 2i equal to 1 by root 5. Okay, so A, B and D are true. So only C is false in this problem. So the next problem, so here given f of z equal to 1 by sin z minus cos z. Okay, so we need to find again which of the options are right. The first one is poles of f of z are z equal to n pi plus pi by 4, where n belongs to z. And the second one, at n equal to 0, z equal to pi by 4 is a simple pole. And the third one, no pole exists, no singularities exist. So we need to check which of the options are right. So the first one, poles of f of z. So the poles of f of z are z equal to n pi plus pi by 4. So we need to check all the options. So the poles of f of z are given by equating the denominator to 0. That is, sin z minus cos z equal to 0. Or you can say tan z equal to 1. So tan z equal to 1 means z equal to n pi plus pi by 4. So at n equal to 0 and z equal to pi by 4, so these are the simple pole, right? Therefore, you can say that A and B are true, right? Because the poles of f of z are given by z equal to n pi plus pi by 4, and at n equal to 0, you can say that z equal to pi by 4 is a simple pole. So clear? So A and B are true. So no pole exists, that is false, and no singularities exist, that is also false, right? So A and B are true in this case. So we will go to the next one. So here given f of z equal to z squared divided by z minus 1 the whole squared into z plus 2. So here the which are the following are true. We need to check the options. The first one, the function has simple pole at z equal to minus 2. The function has no pole and the residue of the function is 4 by 9. The function have no residues. Okay, so we need to check the options. So the first one, limit z tends to minus 2, z plus 2 into f of z. So limit z tends to minus 2, z plus 2 into f of z. So if you apply, you'll be getting z squared, substitute f of z. So what is f of z? F of z is z squared by z minus 1 the whole squared into z plus 2. So just substitute that. So you'll be getting limit z tends to minus 2, z squared divided by z minus 1 the whole square. So as z tends to minus 2, if you substitute, you'll be getting 4 by 9. So this is a finite one and it is non-zero, right? Therefore, you can say that the function has a simple pole at z equal to minus 2. Okay, now you can say that the residue at z equal to minus 2 is 4 by 9. So here the first and the C, A and C are true. That is the function has simple pole at z equal to minus 2 and the residue of the function is 4 by 9. So the function has no pole, that is false, and the function has no residue, that is also false. So the next problem, the residue of the function f of z equal to e power I z divided by z divided by e power I z divided by z into z squared plus 1 at the isolated singular point in the upper half plane. So z equal to x plus I y where y is greater than 0. So we need to find the option, that is minus 1 by 2i, 2e, minus 1 by e by 2 or 1. Okay, so we need to find the residue of this function. So here f of z equal to e power I z divided by z into z squared plus 1. So this z squared plus 1 can be written as z into z plus I into z minus I. So first we will find the residue at z equal to I. So how will you find the residue at z equal to I? These are the simple poles. Okay, here actually if you see the poles are nothing but z equal to 0, minus I and then plus I. Okay, but in this problem, that is if you read the question, the residue of the function at the isolated singular point in the upper half plane. So here you need to consider the upper half plane. Okay, so if you consider the upper half plane, you have to find the residue at z equal to I. So if you find z equal to I, the residue, so limit z tends to I, z minus I into f of z at z equal to I. So if you substitute, you'll be getting e power I z divided by z into z plus I. So as z equal to I, you will be getting z, that is e power I squared. So e power I squared, so e power I squared is nothing but minus 1. So I will be getting e power minus 1 divided by minus 2. So that is nothing but minus 1 by 2e, right? So the A option is right. So this is a part B question. So only one option will be right. So I can say option A, that is minus 1 by 2e is correct one. Okay. So now we will go to the next one. Suppose if you consider the problem under residues, once again. So we all know there are, that is, you can find the residue in three ways. That is by using the Lorentz expansion. That is, under the Lorentz expansion, if you want to find the residue, then you can find the coefficient of z minus a the whole power minus 1. That is, namely a minus 1, right? And then if is it a simple pole, then you can say that limit z tends to a, z minus a into f of z. Is it clear? And then the next one is the pole of order m. So if it has order m, then you can say that d power m minus 1 by dz power m minus 1 z minus a the whole power m into f of z at z equal to a. Is it clear? So using these three ways, you can find the residue of the function. Okay. So in today's class, we have discussed some 9 problems. So I just want you all to try the problems based on the singularities and then the residues. Okay, if you have any questions regarding this, you can ask.
Ma'am,
Yes?
I'm completed, ma'am.
Yes, sir.
Okay. We wish to express our gratitude to our resource person for being with us on this event. Your presence and explanations are very useful for all us, ma'am. Thank you so much, ma'am. I would like to thank our Professor R. Venkatramanan, Head PG and Research Department of Mathematics, for organizing this C4 workshop. Our next C4 session will be held on tomorrow at 11 a.m.